In part one of this series, we explored how ignition timing works and how automatic spark timing works on the Model A4. In this video, I'll show you how to use a timing light and tachometer to measure the timing curve produced by the NUREX automatic timing system. And if you have one of these NUREX devices at home, you can do the same thing and you can check your results against mine. So just as a reminder, the timing curve for a distributor that has mechanical or centrifugal advance is shown on a graph much like this. You've got the independent variable here, which is the RPM of the engine. And as that RPM increases, the weights in the distributor, or in the case of the NUREX device, underneath the distributor, pivot, which rotates the cam and makes the spark come earlier. So what that means is that the measurement here, which is degrees, goes up as the RPM goes up, and so your timing curve is going to look something like this. Now what you're looking at here is actually a previous measurement of the NUREX product, which was done by Jim Kellett in 2006, so 15 years ago as of this video. He put one of these on a Sun distributor tester, and he got this curve right here. So if you look at this curve, remember our initial timing on the Model A is set to 0, so here at 400 RPM, which is a low idle on the Model A, there's no advance, right? 0. And then as soon as you get off idle, it jumps up. Now you're in second gear right here, you're getting up to speed, so the advance starts to kick in. And notice that by the time you hit 1000 RPM, you're up here 24 degrees of advance, so that's about 80% of the total timing is already in by the time you hit 1000. So that's 1000 right up here, right? And with a stock Model A, it's not true if you've made modifications to the engine, but with a stock engine, this range here between 1000 and up here at 2000, this is your power band right here. The total timing is all in by 2000 RPM, and it tops out at 30 degrees. Okay, so these are the results from a NUREX unit that was made 15 years ago. So not necessarily, maybe they've made some changes since then. This is on a test bed, not an actual car. Would you get these results today if you tested it on an actual car? Well, to find out, we're going to need a few gadgets. The first thing you need is a crankshaft degree indicator. NUREX makes this one. You don't necessarily need this one, but this is the one they make. You can see I've got this particular one installed on the front motor mount bolt right here. Just mounts onto that and then goes up. And you want to get it parallel to the pulley. Now for this particular test, you don't actually need this particular indicator, you just need something that will project out parallel to the crankshaft pulley and give you a mark to measure against. Now you need to set the number 1 piston to top dead center. I'm not going to go over that here, there's lots of videos on how to do that, but I will say you need to be as accurate as possible. You need to really try to hit top dead center exactly. And once you do that, go ahead and attach your degree indicator, and then you're going to take a dab of paint, indicate that right there. It's usually white paint, doesn't have to be. And you're going to mark the pulley right next to the 0 mark on the indicator, like I've done right here. You want to get that as close as you can. And this is going to be your timing reference point. The next thing you need is a digital timing light with tachometer. So this one is an Actron CP7529. You can also get the Bosch Fix 7529. It is exactly the same product. This one was 55 bucks on eBay. Now, these are designed to run off of a modern car battery, which means 12 volts. Now, if your Model A has had a 12 volt conversion, you're good to go. But for the rest of you, you'll have to supply 12 volt power. If you have an extra car battery lying around, you can use that, although they're kind of heavy. You can also buy 12 volt lead acid batteries at hardware stores for under 20 bucks. You do not need a lot of capacity for this test. You just need something that can deliver 12 volts. I mean, you could use 8 AA batteries strung together. What I use is 2 6-volt batteries, because I have these guys sitting around. I use them for testing Model A coils and horns, lights, all the other electrical stuff. So I have these lying around. So you're going to take 2 6-volt batteries, and you're going to use a simple wire to connect them in series. So you see I've got my one black terminal connected to one red. Take the Actron. Okay, so you're going to take the Actron's leads, red to red, black to black. All right, and there you go. Got a 12-volt battery. So this is a timing light that has an inductive clamp. The way these work, got this clamp here. This is separate from the battery connectors. Take this clamp here, and you put it over the #1 spark plug connector, which on a Model A usually looks like this. Now when the spark on the #1 cylinder fires off, there's current in this plug wire, and there's an inductive coil right here, and the current in the plug wire induces a current in this coil, and that triggers a xenon strobe light right in there to flash, which illuminates the position of that white dot on the crankshaft pulley at that exact moment, and that tells you how advanced the timing is. However, like all modern timing lights, this clamp is designed for big, fat, insulated, modern spark plug wires. It is not designed for this. So this is, as I said, a Model A spark plug connector. It has no insulation whatsoever. If you try to clamp this around this, not only will it slide around, but you will totally ground out that spark plug. The cylinder will misfire, so your engine's going to run poorly. And meanwhile, because the current's going to get transferred into here, and it's going to get transferred into this, which you are holding, you are going to get shocked with 15 to 20,000 volts 7 times a second. I have gotten shocked this way. It's not fun. I don't recommend it. So this brings me to the first of 4 critical warnings in this video. You must insulate the inductive lead from the spark plug connector. So now fortunately this is pretty simple to do. What you're going to do is get some 1/4-inch clear vinyl tube, and you're going to cut a slit in it. Hopefully you can see that. So let's put a slit in it, and you're just going to slide it over the connector. So there you go. But now it's still not thick enough, because if you put it on now, the lead is just going to slide right down, and it's going to ground itself right at the plug. So, and then it's going to shock you again. So what I do is I take 2 little garden hose washers and slide them over the end right here, just like that. And now, when you put the lead on the wire, just going to go like this. Now it'll stay put. You can see I've still got the connector right up close to where that inductive coil is, so it'll sense that charge just fine. So here's the engine we're going to run the timing curve test on. If you've seen my previous videos, you'll recognize this high compression head. The reason that my connectors are different is that this head relocates the spark plug holes. So the normal stock plug connectors won't work. These wires I actually made myself using Model T plug wire and Model T brass terminals. But it works pretty much the same. So you've got your number one spark plug right here, and so you're just going to clip this over this wire, and I like to hang this up over the radiator support rod. You really want to try to keep this away from the engine, right? Don't let it fall, because if you just sort of let it dangle, what's down here, the manifold's going to be about 1,000 degrees, so that's probably bad for your wire. So now this car has been equipped with the new Rex automatic timing system. You can't see it, of course. It's down there inside the valve cover if you use your X-ray vision. And the one that we're using here was manufactured in 2018. So that's a newer generation of the device than the one that Jim Kellett tested back in 2006. So I'm very interested to see if the timing curve on this has changed at all. So to get set up for the test, we've got our inductive lead right here, got our wire, and that's going to go over to the Actron, and then the Actron is connected to my makeshift 12-volt battery right there on the running board. Okay, so I'm going to briefly cover how this is all supposed to work. All right, so you're going to start the car. When you start the car, make sure you've got your spark lever all the way up. That's sort of like the whole point of what we're doing. You'll have to bring your throttle lever down to get started, but then let the engine warm up and get it to a point where you can bring the throttle lever all the way up. So now you're just idling, it's warm, it's idling on its own. Now you're going to hop out and you're going to run around the car and get your timing light. So then you're going to grab your timing light, and it won't be flashing 000, hopefully it won't while the engine's running, because it'll be getting a signal from the inductive lead. But just note, see it's got this button here, RPM/advance. It won't strobe unless that is set to advance. So when you're registering the RPM, it won't strobe, but you'll get the RPM, and then you take the RPM measurement and then you flip it over to advance and make sure it's on 0. And then when it's on advance, you're gonna look down here, and you want the strobe to illuminate that pretty much just like it looks here, with the white dot right at 0. So once you've done that, you're going to record the idle RPM and the initial advance, and then you got to write it down somewhere, on a computer, post a note on your phone, whatever. And then either with a buddy or by reaching in through the passenger window here, you're going to move this throttle lever ever so slightly. So you're going to come over here and you're going to move this throttle lever a teeny tiny amount, whatever the smallest amount that you can, right? So not even a full notch. You want it like on the little hump between these notches. And the reason is that we need a lot of data points to measure the curve accurately, especially at the low end. We need to make our incremental changes as small as possible. So you move the throttle a little bit, just half a notch, and then you repeat. You measure the RPM and the advance again, and then you move the throttle a little bit more, and then you measure again. And you just keep taking measurements until you get to 2,000, 2,200 RPM, wherever it is you want to stop. Now this brings me to the second of our 4 warnings in this video. You must be able to lock your throttle lever in position. So you see how my lever is pressed against the ridges of the détente here on this quadrant. If your lever doesn't sit right up against those détentes, it won't stick where you put it. It'll migrate up and down as the springs on the throttle control lever kind of pull it back into a position, and you'll get bad data. And you don't want bad data.
Before you start, I recommend doing a test run, just to make sure you can get good readings with your tools and to make sure the car is cooperating. The goal of your test run should be to successfully measure the initial timing. You need to take a reading that gives you 0 degrees advance. If you can't take that reading at 0 degrees advance, you can't be sure that your points, the auto advance, and your timing light are all calibrated correctly. Now, to get that 0 degree reading, you're going to have to get your idle down really low, down to 400 RPM. A lot of folks do not normally run their idle this low. But I mean, look at this graph, right? By 500, the advance has already jumped 8 degrees. So this brings me to the third of our 4 warnings. You must adjust the car to show a 400 RPM idle and 0 degree advance.
So how do you get the car there if you don't start there? Now, the first thing that you need to do is get the idle down. And usually the way to do that is to turn out the throttle stop,
which is right here. Keep in mind, you're going to be watching the RPM on your timing light the whole time. So turn out the throttle stop gradually. And if you can't get it to 400, try turning in the idle mixture a little bit and then turning out the throttle stop again. And if it keeps stalling and you can't get it down to 400, then unfortunately you're outside the scope of this video. Now I should say this is a Marvel carburetor. It's not the stock Zenith or Tillotson. This is a Marvel carb. This was actually built for me by Jim Bullock, who passed away from COVID 2 days ago as of this filming. He was probably the best Marvel car builder in the country. Certainly one of the only ones. It's really a terrible loss for the Model A community. And anyway, so of note, if you have a Marvel carb, to richen the idle mixture, you turn this out. But if you have a Zenith or a Tillotson, to richen the idle mixture, you turn it in. So just keep in mind which carb you have is going to dictate which way you turn this. Now, what do you do if you get it down to 400 RPM but you're not showing a 0-degree advance? Well, maybe you need to time it again. But the first thing that I would try is actually to disconnect the spark advance rod here. And adjust your upper plate by hand, and usually that'll let you fine-tune it and so that you can get it right on that 0. You don't need the spark advance rod for this test anyway. So that's all you need to know before starting this test, except for one thing, which is the fourth of our 4 warnings. In this video, you must do this test in a well-ventilated area. I don't want anybody dying of carbon monoxide poisoning doing this test, so I'm going to open my garage doors and back the coupe out slightly, and then set the parking brake, and then we'll be ready to go. Sorry about the bad camera angles. Here I needed to use both hands and also to move around, so I improvised a kind of a chest mount for my phone. So you're going to start the car and then move around to the engine bay, and the first thing you're going to do is just confirm that 400 RPM idle. At this point I'm going to lean in and adjust the upper plate by hand to try to align this white dot that you see with the 0 on the degree indicator. And then I'll know I've got 0 degrees initial timing. So I take that initial timing and record it on my laptop, which you can't exactly see because of the bad camera position. And then I'm going to bump the throttle up slightly. So now the first surprise I got was that there was no movement of the initial timing at 450 or anywhere before 500, which is what I was expecting. It was hard to get consistent incremental throttle advance. Despite my best efforts, it really helps here if you have a buddy, somebody who can sit in the cabin and adjust the throttle for you and, if possible, write down your results. Now here at about 640, I finally see the timing start to advance. You can see a white dot in the center of the screen moving up and down. That's me adjusting the advance that's shown on the timing light. And when it lines up with 0, then you've got the correct advance. Make a note of the advance degrees and the current RPM, and then write those down. And then just keep incrementing and keep writing down your results. Again, it was sometimes hard to advance the throttle smoothly without a buddy.
Now at this point, my makeshift 12-volt battery started to come apart because of vibrations in the running board, and I actually had to move it over to an adjacent table. Once I got up over 2,000 RPM, I actually started to get bad readings on the timing light, and I had to stop. Now, my best guess is that the inductive coil on the timing light was picking up electromagnetic interference from the spark current on the number 2 plug. So here are our results. You can see this is the expected curve based on the 2006 experiment, and then here, overlaid under it, is the curve we actually got. What you're seeing, or what I'm seeing, is a significant delay in where it starts to advance. So it's starting to advance somewhere between 550 and 620. I didn't have the precision to really figure out exactly where it started, instead of between 400 and 500, as in the 2006 edition. The other thing that you see is, so after the delay, it starts to catch up, and then right about 1200 or so RPM, it settles in, and at this point it's just about 1.5 degrees behind the expected curve. And I think probably it would go off. I had to stop measuring at 2000 because I was starting to get bad data, but probably it's going to go off and add another 0.5 degree or full degree here, maybe up to about 2300. So to what can we attribute these results? My guess is a stronger torsion spring in the unit that I've got versus the unit in 2006. And I don't know if that's by design or just variations in the manufacturing, but a stronger torsion spring attached to that gimbal shaft to resist the pivoting of the ring would give similar results to this, waiting longer to begin the pivot, and then at each given RPM pivoting a little bit less than the reference curve. So now what? Well, that's what we'll do in part 3. Now that you've got this information for your engine, what do you do with this information? And also, hopefully, we'll get to take a look at a Model B distributor. Remember, I talked briefly in part 1 about how Ford used the centrifugal advance mechanism in the Model B. So we'll take a look at that, and I'll see you guys then.